Okay, thank you, Professor Matthias, for the introduction, and thank you to the organizers for giving me the opportunity to present this job, which is a team effort of the people listed in here. I'm glad to say that all of them are present in the audience, so if I don't manage to deliver all the knowledge that I want to say here, all we will be completely happy to continue the discussion later on. I will be the next in the list of trying to show the importance of patchy charge distribution in protein solutions. But the little bit twist that I'm going to propose here is that we will see how this affects the pH during dialysis process. So I know that you are familiar with dialysis, but I just will go briefly through it, such we ensure that all we are speaking the same language. Basically, initially we have two compartments. One which is called the retentate, where we will have the protein solution or the macroion solution that we would like to dialyze. For instance, one of the beautiful monoclonal antibodies that were presented by Fabricio. And together with them, we will have small ions also in this retentate. They will be divided by a semi-permeable membrane from the outer container that we will be calling permeate. The idea is like once it reaches the equilibrium, if you follow the color code that I put in the slide, at the beginning it happens that you have a dark green color related to the concentration of small ions, that in the equilibrium we will expect to have more or less similar concentration in the inner and in the outer solutions. In real life, it doesn't happen like that. Actually, we have an uneven distribution of concentration of small ions, and this was observed for the first time by Kelvin. Then he sent a letter to Donnan, and together with together with Donnan, they derived something that we call now the Gibbs-Donnan equilibrium, which basically explains this uneven distribution of small ions as an effect on the presence in the charge of the proteins or the macroion. What does it mean? You can imagine that if you have inside the retentate the protein with charges, they need to be counterbalanced with the small ions, that it should be taken from the solution in the outer, right? So we will talk in this ratio of concentrations. We'll describe it as the distribution ratio, capital D. This is the expression derived by the Donnan-Gibbs theory, that it actually says that this distribution ratio depends on two main factors. One is the concentration of the charges in the protein, and the second is the ionic strength. Now, it will not be a surprise that if there is an uneven distribution of small ions, that we will have also a difference in pH, because at the end of the day, H plus is again a cation, right? So we expect to have a more concentration of H plus ions in the case that those guys are negative than the outer solution. We will use then this trivial equation that relates the delta pH with the distribution ratio of cations, knowing this expression, right? Now, the problem is like the experimentalists are trying to use the Donnan theory to represent the experimental results. Here I'm showing they use membrane separation to concentrate the solution of two different monoclonal antibodies, A and B, orange and black in the plot. Here we see the pH in the retentate against the concentration of the protein. The dashed line corresponds to the pH in the permeate, the other solution. First, let's focus on the experiments. You can see that clearly it deviates from the pH in the permeate as expected. And this deviation increases while concentrating the solution, right? Now, if you see the solid lines, which is basically the prediction that they do using the Donnan theory, you can see clearly that it actually resembles nicely only one of the monoclonal antibodies, but not the second one. In the second one, you see how the deviations from the experiments increases also with the protein concentration. Our expertise is in charge regulation. I work in the group of Peter Koshovan, and we believe that if the problem is that the way how they model this protein, you see the rabbit in the previous presentation as well. So here they use just the sphere, and they assume that the sphere has an homogeneously charged on the surface. Basically, with this, they are disregarding the charge regulation in the protein. So we also know from many other talks in here, for instance, Ronald or Stephanie, they show how this actually affects, because if you have a system with charges scattered in the surface instead of homogeneously distributed, you will expect that the local electrostatic potential around these charges will affect. Depending if they have an attractive interaction, then we expect that the ionization degree will be increased. But if instead we have likewise charges, we will expect to have a repulsion, and then this ionization degree will be decreasing depending of the local electrostatic potential. If we put this phenomena into the model, basically what we propose is like, let's treat the rabbit as a sphere. when we have the shape of the monoclonal antibody will be represented by the radius of gyration, will be this central core that we see here, and it will contain, it will represent just the excluded volume of the protein itself. Now, the ionizable group that it will be in the surface of the monoclonal antibodies, at the beginning, we just wanted to put them on top of this core and representing only the electrostatic, so the Coulomb potential. This is completely unrealistic. It's just one proof of concept model such that we know that maybe we can represent or we can describe these deviations in the experiments with charge regulation. First, we try to reproduce this using the simulation method of grand reaction Monte Carlo together with Langevin dynamics. Basically, Langevin dynamics take care of the configurations in the system, changing by thermal fluctuations. And with the grand reaction ensemble, we do both the simulation of the acid-base reaction of the groups, as well as the exchange of the ions with a virtual reservoir. Now, if we want to reproduce the Donnan theory, here is what we expect. So basically, we just move our pH to one point when actually the nanoparticles will be always charged. That means we will not have charge regulation. If you take the expression by Donnan, but given Donnan, basically, if we go to the extreme where the concentration of the ionizable group is big enough in comparison to the ionization strength, this expression reduces to this single in here, where the distribution ratio is directly proportional to the concentration of the groups in the protein and inversely proportional to the ionic strength. We see here this plot of distribution of ratio of sodium against the concentration of the protein, that if you increase the concentration, then likewise it will increase the distribution ratio of cations. But if you focus in the colors of the plot, which represent the ionic strength, if you increase the ionic strength, going from red to blue, you see how the distribution ratio decreases, resembling what Donnan said at the beginning. Now, we want to understand what happened around the charge regulation. So let's reduce the pH to a point where actually these charges can fluctuate from ionized and non-ionized. This is what I'm showing here. We are trying to represent these results in terms of the ionization degree against the pH in the permeate. The black line here is the Henderson-Hasselbalch equation. We already know this behavior so good. The dashed line next to it, it corresponds to this delta pH arising from the uneven distribution, the Donnan contribution. But we see that with our simulation, the dotted line, we see an extra shift from the Donnan. And this is actually due to this electrostatic or to the repulsions that these likewise groups are actually affecting the system. Now, to move from ionization degree to delta pH, we already more or less understand the chain. Basically, it consists in, if we have a reduced ionization degree because of the repulsions, then we will have a less concentration of the ionic group in the protein. If we have this less concentration, we expect a less distribution ratio of cations. And then if we have a less distribution ratio of cations, we expect a less delta pH. Basically, the summary is like Donnan is overestimating the delta pH in comparison to what charge regulation can do, which is effectively decrease this delta pH. Now, we wanted to play a little bit with our model because now we know that we can simulate this charge regulation. But how we can play with this? We just say that we will have a parameter which is called the degree of patchiness. Basically, we just start to move the ionizable sides from occupying all the sphere into moving into, for instance, half of the sphere, and the other half will be without ionizable groups, to, for example, here when the 10% of the area is occupied by the ionizable sites, and the rest of the area doesn't have. Basically, we are just changing the distance between those charges, and you might expect that this will be reflected in the ionization degree, again, showing a stronger repulsion effects, and therefore, we understand the chain, it will end up in a smaller delta pH. So basically, again, Donnan is overestimated, and if we have these charges closer and closer, more patchy in the system, we will have an increase in this effect on the delta pH. Now, nice so far, but we all know that proteins don't only consist in negatively charged, and not in the case of monoclonal antibodies. We saw nice maps by Fabricio that they actually are scattered around. That's why we wanted to do a little bit more realistic model, not into the shape. We are expecting that maybe we can do it in the next step. We let shape to a side, and we want to focus in first, adding basic groups, so we have both positive and negatively charged. Also playing with the charge distribution, but in this case, we just can do it moving the patches in the surface in different positions. For instance, Janus-like nanoparticles, looking like the inverse Patchy that were shown by Peter and that it was originated by Emanuela. We have here all the negatively charged in one pole and the positive in the other. We also propose one Y-shaped distribution, similar to what Fabricio shows, that they will be in the tips of the arms. And also we propose this belt model when actually the negatively charged are in the poles, and in the equator we will have the positively charged. Now, also we wanted to reproduce better charge density. You might expect that the previous example that I showed, we were exaggerating too much, that we will put just all the charges in the 10%. It's not that realistic. But now we study a characterization done by Wellat, where he shows that the size more or less of these antibodies are 5 nanometers, the charge density is 1.16, the fraction of acidic sites against the basic is 0.58, and they have more or less 364 groups. We try to reproduce charge density because it's something that we can do easily, because we cannot go to reproduce or to simulate all the total groups in the simulation box. Then it will be so expensive computationally. So if we want to set this guy similar with less total of ionizable group, we need to sacrifice the size of the sphere. So we will have a smaller nanoparticle, but having the same charge density. Also, we changed the PK set. This I will not go too much in details. If you want, you can ask later. But basically, we will have here 4 types of amino acid. One of them will be completely fixed, more or less resembling what will happen with, for instance, arginine and aspartic acid, that they will be in the stream of the pH curve. They will be fixed, more or less in the normal pH range, but they will be also 2 kinds of amino acids that will charge regulate, one acidic and one basic, and they will have different pK. Now, the results. First, as I showed before, let us start trying to understand what happened with the ionization degree, and then we will be moving towards understanding the difference in pH. This I'm showing first the Janus-like nanoparticle. The solid lines against in the Henderson-Hasselbalch equation. We know now that if the plot, this variation in color, it's due to the concentration. I will not go to talk about this because I don't have enough time, but basically you see that generally all the plots are below the ionization degree in both cases, acidic and basic. So that represents the strong repulsions that is happening under this charge regulation. Basically, this translates into also a difference in the net charge in comparison to the ideal case in black here. The points in purple are downward and upward titrations of a monoclonal antibody. So we see more or less that it resembles the shape, not completely. We don't want to say that it's a quantitative comparison, but still, we just wanted to have as a reference. Now, you might think that the key parameter here is like, how is the balance between the attractions and the repulsions? Here, the repulsions dominate. But do you think that it can happen that we have a charge distribution such this balance changes? And the answer is yes. Actually, if you change to the wave-shaped nanoparticles, you see that now this plot that before you show clearly explicitly repulsive, it actually changed the shapes and crosses the ideal, going to the above the ionization degree. That means we go from a repulsive regime, crossing the equilibrium, going to an attractive regime. This is quite interesting for us because that means that it will also have consequences in the net charge. And as we understand before, if we change the ionization degree and we change the charges that are in the protein, therefore we will have also changes in the difference of pH. How this works, this is kind of the kind of plot that we showed from Briscott, experimentalist. Again, we have the pH in the retentate for 3 different pH in the permeate at 5, 6, and 7. Why this pH? Because it resembles 5, 6, and 7. We want to understand what happened in the repulsive during crossing the equilibrium and after. Basically, with the yellow one correspond to the wave shape. You see that before it's below the ideal. So basically, again, Donnan is overestimating this prediction. But now, when it goes actually on the titration, the ideal curve, we see that we can use Donnan theory to reproduce it because it kind of fit in with this theory. But if you go to the other side, we will find out that when attractions are dominating, then we will have overestimation with the simulations in comparison with the Donnan theory. And this is not happening for the other charge distributions. you see that for the Janus-like and the belt, they are always below the Donnan theory. Basically, we just have a quick flashback of this. With what they find out is like some of the experiments are well reproduced by Donnan theory, some of them are being overestimated. More or less, you can see here that the wave shape will actually be fitting this formula. This could be like related to this guy, but the other ones are below the Donnan theory, which basically more or less resemble this. I'm not planning to do quantitative again comparison. I'm just showing trends, and that charge regulation might have something to do with this problem. For concluding, I don't know how much time I have. I think I don't rush that much. But basically, we develop a feasible simulation approach to understand and simulate this dialysis of protein-like nanoparticles. Not necessarily, in this case, monoclonal antibodies, but we can move to other kinds of protein systems. We take into account not only static repulsions and Donnan effect, but additionally, we are taking into account the electrostatics in the system. Additionally, we can confirm that Patchy charge distribution significantly affect the pH in the solutions due to these attraction and repulsions. And also, we see that how coarse grain simulation has a great potential to describe and predict these deviations. The importance of this, that maybe it was lacking in the motivation, but now it came to my mind with the Fabrizio's presentation, is like he is in the point that he's worried about mostly the administration process. We just get a step back into the industrial point. So yes, when we are concentrating a solution, we wanted to understand that these differences in pH are so delicate. They will like to have an homogeneous solution of monoclonal antibodies. They will not have aggregates. So you might see and you might say, okay, this is a small change in the pH, it's just 0.4 units. But in theory, 0.4 units can differ into having a homogeneous solution or a heterogeneous distribution. That's why I wanted to show more or less what's coming for us. Basically, with this model, we also can tell a little bit about how is the clustering aggregation processes, because basically, this is a video says more than words. Basically, depending on the concentration of the guys and the pH, you can start to see how in the simulation start to form this kind of nets or like metastable states of the agglomerates of the proteins. Here I'm showing a really diluted system, but if you move into a more high concentration of the proteins, you will see how they start to form a columnar or like a stable. Well, we cannot say stable completely, but at least we can move into that direction in the next of the research, such that we can say yes, 0.4 units of pH can actually trigger phase separation. I would like to acknowledge my research team in Prague, also my supervisor and advisor that they for a nice discussion, as well as Rita and Till Biscott, the funding agencies. And muchas gracias por su atención. I will be happy to answer any questions that you have. This is the QR code to the article.